Today I'm going to solve LeetCode question number 22, generate parentheses. Given n pairs of parentheses, write a function to generate all combination of well-formed parentheses. Okay, so you have given n equals 3, so we can have 3 pairs of parentheses. And they have to be in valid order. So these are all the valid orders here. So this is not valid parentheses, okay? And yeah, so let's look at the conditions where the combinations of the parentheses are valid. So when we just started out, so basically just to iterate, we can have 3 open parentheses and 3 closed parentheses in total, and we can use this in our function here to keep track of how many parentheses we've added. Okay, so now let's look at the different valid parentheses or invalid parentheses. So we initially start out with 3 available open parentheses and 3 available closed parentheses. Can we add a closed parentheses? No, this is already an invalid string from the start. Okay. For closed parentheses, we need to match an open parentheses. Okay, so closed parentheses needs matching open parentheses. Okay, so we can start out with an open parentheses. Great. And then this is reduced to 2. Okay, so what can we add here now? Can we add a closed parentheses? Sure. Can we add another open parentheses? Yeah, that sounds fine. Let's add an open parentheses. So available open is 1. Can we add a closed parentheses? Okay. So now this, and then we reduce that to 2. And then this is one well-formed set. 1 out of 3. And now, can we add an open parentheses? Or can we add a closed parentheses? Sure, we can do that. This is now 1, and now we only have one choice for open and close. We cannot do this, obviously. So we have to do this. What if we did do this? Then this guy would be 0 here, and the closed would be less than open. So basically we want closed to be greater than or equal to open parentheses, never less than open, in order for it to be well-formed parentheses. Okay, so yeah, if we look at these conditions and build our decision tree here, let me erase this for more room. So if we have n equals 3, so open equals 3 and closed equals 3, we can have this guy. Okay, so that means open is equal to 2 and closed is equal to 3. Okay, and here, can we have a closed? No, we cannot. Can we start with closed? No, we can't. And let's build out from here. So we can have this open, add on another open, or for this open, add on a closed. Where here open is 1 and closed, how many there's left? There's 3 left. Okay, and here open, how many left? 2, closed, how many left? 2. Okay, and then once we go from here, our decision tree also broadens. So we can have this already. What can we do? We can add another open. Okay, and then open count would be, or number of open left would be 1, and closed left would be 2. We cannot do closed here. Okay. And here, what can we do? Well, we can close it or continue with our open. Okay. And if we continue with our open here, there's no choice but to add a close because we all ran out of open. Okay, and then this will branch off and then add 2 more closed. And here, what we can do is add another closed or add another open. Yeah, so that's how where it's gonna go. And if either of these equal to 0, if both of these equals to 0, that means we've exhausted all our available open and closed parentheses, and we have a result that we can append to our array. Okay. This is a good example of a backtracking or dynamic programming problem, where if given where we try out different combinations, solve subproblems first, and if one subproblem turns out to be invalid, we scrap that and continue on from the valid point. Okay. So if you had like here, that's obviously invalid, and then we continue on from here to a valid case. Okay, now to code this up. So since this is a backtracking solution, its runtime would be some sort of exponential. It's pretty complicated to figure out, but usually with backtracking it is some kind of exponential, especially without memoization, which we can't do here because we need to backtrack and do generate all combinations. Okay, so our result array will be that, and then we're gonna have def backtracking, and this is gonna be recursive. So this will have our num of open available parentheses and number of closed available parentheses. Okay, and our base case here is num open equals 0 and closed equals 0. That means we found a valid combination here where we used all parentheses, where we generated n parentheses. Remember, n parentheses made out of n open parentheses and n closed parentheses, so we're gonna result.n and string. Okay. And this is going to contain our parentheses string here. What are some base cases? If that is less than 0 or that is less than 0, we can't dive into negative number of parentheses, then we stop the execution there, just return. And also, if number of closed parentheses is less than the number of open parentheses, also stop in our tracks there. So like if you have this parentheses and n equals 1, and then we have this parentheses, then the num close is going to be 0, and here, which is less than 1, number of open. So that's obviously in the valid case, so we're going to return. Yeah, and otherwise, what we're going to do is two paths, either add the open or add a close parentheses. So we're going to do backtracking. Let's do the case where we add a parentheses. Nice one. Close, and parenting plus, and open parentheses. Okay, so that's one path we can take in a decision tree. And a second path we can take is adding a close parentheses. Okay, and if the parentheses string is if these two conditions are met, then obviously the parentheses string is invalid. But if this is met, then obviously the parentheses string is valid, and we append that to the result. Okay. So now in our main function, we're going to call backtracking. Num open, number of available open would be n, number of available close would be n, and initially this would not blank, but that would be an empty string because we're going to build upon it in the backtracking function, and then return result. Okay, let's try compiling it first. Okay, I'll use other example cases. And while this is an exponential runtime, there's only constraint is n is bounded between 1 and 8 and all inclusive. So the runtime won't be very slow because we will have a limited number of n. Let's try running it. Okay, thanks for watching.